All right, so this is more of a classroom activity, but I'll give you a chance to kind of do it at home on your own. So what I have here is I have a meter stick, and I've gone ahead and drilled a hole at 1/5 the length, so at the 20 centimeter mark. And then I'm gonna go ahead and just let it swing. And I used my stopwatch just off camera a second ago, and I timed how long it took to make one period, and I got 1.53 and 1.50. I probably could have timed it to do several periods and then tested that, which you have a video of it doing this now, so you could easily do that same strategy and see what you get. And what our goal was is we wanted to derive the moment of inertia of the stick about that point. Some of the class also did it about 1/3 the length instead of 1/5 the length. And then we want to calculate or derive, I should say, the period about that point as well. So what I'm gonna go through today is I'm gonna go through those calculations, and I'd recommend that you try and do it first, and then come back to the video. So here we go. So deriving moment of inertia for a uniform rod about some point. That's going to be where we start. So I'm going to start with the equation they put on our equation sheet, the integral of r squared dm. Now we tend to not use this equation because typically we break up this dm. So let's think about what we do there. So mass is equal to density times volume. And so we say that every little piece of mass is equal to the average density times any little piece of volume. And for a uniform stick, that little piece of volume changes a little bit. So now we have the density times the cross-sectional area. Because it's a uniform stick, it's going to have a uniform density. It's also going to have a uniform cross-sectional area times the length of the stick, which we could put in as dr in this case. Sometimes you'll see us use dx and use an x squared here, just to represent that it's a one dimension x, as opposed to more of a three-dimension r, but we're good with that. The other thing we'll do is when it's a non-uniform, this density times cross-sectional area becomes a linear mass density lambda equation that we can substitute in there. So just something to kind of keep in mind when you do see this dm, that we do have to make those substitutions. Now because this is a linear object, if I go ahead and integrate my dm from 0 to the length, I'm going to end up with pal, and so pal is going to be the mass. If I have a function here, I'm going to have to integrate that function across the length to figure out that mass of that object, because we're going to go ahead and pull that mass out later. But for us here, we're looking for our pal. All right, so let's make that next step. So I have I is equal to the integral of my density times cross-sectional area r squared dr. Now to determine my bounds. So how we determine the bounds is you draw your little bar, you identify your axis of rotation. So this is my axis of rotation, and I make it x equals 0. So for us here, we're going about the 1/5 length. So this here will be at L over 5, and the negative will be this x endpoint, and this x endpoint will be for L over 5, or 4/5 L. This tells me what my bounds are going to be on that integral. So the group that had the 1/3 the length, so this would be negative 1/3 and positive 2/3. The math does go easier on that, but I wanted to show this one. So I here is going to be my integral from negative L over 5 to 4L over 5 times density cross-sectional area r squared dr. Okay, so we start plugging in our stuff here. So we end up with 1/3 times density cross-sectional area. And now we got to evaluate that r cubed from this point to this point. So now I have 4 cubed, 64L cubed, divided by 5 cubed, 125, minus a negative L over 5 cubed. So I get negative L cubed divided by 125. Okay. What we see coming out of here is we have 1/3 times 65 1/25 density cross-sectional area times L cubed. But instead I'm going to make that L times L squared so that I can find my pal. Type this in your calculator, hit that fraction button, and you end up with a fraction of, what was it, 13/75, of course, right? 13/75 ml squared. If you go ahead and do it for the 1/3 length, you should end up with, what was it, 1/9 ml squared for our I value for that point. Okay, so now I have my I value. Let's go over here and find it for the period. So now we want to derive the period. Okay, so I'm going to use torque. So the sum of the torques is going to be I alpha. I know I, that's going to be helpful. Again, with simple harmonic motion, our goal is we want to have it fit the equation that alpha is negative omega squared theta. We want it to fit this criteria. If that doesn't make sense to you, go back. We got videos before this that kind of go through that idea, why that's true. So now we need to find our torque. So remember, torque is perpendicular, so I'm going to have this part here, which is going to be my mg times the sine of theta, where theta is the angle that my meter stick is making with the vertical. All right, so that is going to be producing my torque. So I have mg sine theta times how far away it is, I'll just call that d for now, is equal to I alpha. One thing we end up doing here is we're going to make a small angle approximation. And when we do that, we need to indicate that if the angle is this way, the torque is the opposite way. So we'll need that negative sign on there. So we end up with negative mgd times theta is equal to I times alpha. Again, here we made a small angle approximation that the sine of theta, I should write it down, is approximately theta, and that theta and the torque are opposites. So in this vector kind of scheme here. And so now I have mgd divided by I negative theta equals alpha. This is my omega squared. So now I can go ahead and use that to find my period. Okay, so my period is going to be 2 pi divided by omega. So I need the inverse of the square root of that thing. So I divided by mgd, take the square root. Now the only step left is I have my I value. The length of my meter stick is 1. That's kind of convenient, right? And then the d value. How do I find that d value? Well, if this is 1/5 the length, in order to make it to the half mark, it's going to be 3/10 the length. So for my 1/5 L portion, my d value is going to be 3/10 L. Okay, so now I can plug in some information and see what we get here. So I have 2 pi times the square root of 13/75 ml squared. Again, remember that L is just going to be a 1, divided by mg times d, which is 3/10 L. Kind of fun information there. The m cancels out, so I didn't even need to know the mass of that. And so my period, when I plug in an L of 1, G of 9.8, because we are still here on Earth, I get a 1.52 seconds. And again, when I was doing my timing, I got 1.5, 1.53, which is remarkably close considering the air and the human timing. If you did it for the 1/3, you should get a 1.64 seconds. Fun little fact here. So let's move over to this thing and think about something. That if I move it up, like that period is going to get longer. And if I get it to the middle point here, it would actually spin forever. It wouldn't actually oscillate. It's not until I move it just a little bit away that I get a really slow period. So, but as I move it even above this, let's imagine I had some way of connecting this without mass, that physical pendulum period is also going to get longer. So somewhere in here is a minimum. So if you're a nerd and you want to hang out for another minute here while I set up a problem for you, let's do that. Let's move this out of the way quick. There, moved it out of the way. So what I want you to think about is I want you to use the parallel axis theorem to find the minimum point where the minimum period, and where is that location at. So let's kind of look at this equation over here that we set up, that period is equal to 2 pi times the square root of I divided by mgd. And so my period is going to be 2 pi times the square root of, use our parallel axis theorem, so it's 1/12 for a rod about its center of mass, plus md squared, all divided by mgd. I see my m's cancel. Now I have a function for the period in terms of this distance d. So go ahead, take that derivative with respect to d, and then set it equal to 0 and solve for d. Not to spoil your fun doing that, but your d value, where did I calculate that? Whoop. Your d value should come out to be 0.2886, or another way to think about that is 0.211 meters from the end, which is darn close to our 1/5 point. So it came out to be 1.53 seconds was the period. So kind of a fun little side calculation for any of you nerds out there like myself. There you go.